So far in this lecture, we've been mainly dealing with one part of how we can do machine learning, namely by unsupervised learning. And unsupervised learning means that you have data and this data is not labeled. So what you want to learn from the data is not yet in the data that you have. And today we start the second part of this lecture, and that means we focus on supervised learning. Supervised learning means that the data points that we have labels attached to them. And so what we know, at least for some training data, some data that we use for training, what is the expected outcome? And now we can still further divide that and ask, what is this outcome? And one possibility is that this outcome is a label or a categorical variable. So this categorical variable, for example, yes, no, male, female, rather than a number. So that's the, did you get the shot?
Oh no, apparently you have to come there at like at 8 AM, then wait for an hour, then get pre-registered number, and with that pre-registered number, you show up later on.
Okay. At least at my PE, I'm able to just go there and get the COVID shot and the flu shot at the same time. So it's, I'm still hesitating a little bit. I was supposed to be there today, but I wasn't so sure if I would survive the lecture. Okay, great. Okay. So I was just not saying much until now. Basically, we have the different kinds of learning: unsupervised, supervised learning, and now what we want to go is to go into supervised learning. And within supervised learning, we have different categories of what we can learn and what we can predict. So we start with the situation that what we want to learn or what we want to predict is a categorical variable. It's not a real number or so, but it's a yes, no answer. It's a category, male, female, or so. And this task is usually called classification. So we'll now first talk about classification. Different kinds of how you can classify data, a little bit related to clustering. And then the next step, we will do regression, which is the prediction of real valued training data. So classification is not real valued, it's a yes, no answer, it's a category. And so let me share the screen. It's installing something. Okay, wait. Here we go. Yeah, so we're in the framework of supervised learning. That means we have data that is labeled for us. We know this yes, no answer. Yeah, and our task is now to predict this yes, no answer or this label, this category for new data that are arriving. Now, for example, a classical example is you work at a bank and this bank has lots of data on transaction, their customers, what they do with their credit cards and so on. And now your task is to detect credit card fraud. Yeah, and you might have data points of the following sort. So for a certain time period, you might have first dimension, the average amount of cash that is drawn. And on the second dimension, you might have the frequency of withdrawals. Now, you might think that if someone steals your credit card, there will be a different, higher frequency and a higher amount of cash that is drawn from your credit card. So that's a classification task. because for a given time period, a different time window, you need to decide whether this card, this data point, or this customer is subject to fraud, yes or no. Yeah, that's the classification task. And our task is now to learn a rule that allows us to predict the labels of new incoming data from the data that we have at our disposition at this credit institute. Yeah, so that means that visually we want to draw a line in some high dimensional space or a hyperplane or a manifold that separates these data points into a point that's have one label and into points that have some other label, points that correspond to credit card fraud and points that correspond to a normal behavior. Yeah, that's a typical task of classification. Other class of task of classification is of course spam emails. As we the first lecture I showed you, you get spam emails. That's some high dimensional data points, the words that are in these emails, and now you have to classify them according to some learned rule into spam or non-spam emails. The general aspect also is text classification, but also other sorts of classifications of customers, for example, and so on. So, and in order to do that, we're assuming that the data is drawn from some complicated and unknown random process. So what we're trying to infer is a statistical way of dealing with this data. Yeah? So in order to do that, we have to first familiarize ourselves with a little bit of statistics. I know that Ivan already showed you, gave you a rapid introduction to statistics. And so I'll just briefly recapitulate some aspects of Bayesian statistics and multivariate statistics, just that we're on the same page. And of course, many of you or some of you will have already heard of these things in the past. Okay, so as basically I've been repeating through this entire lecture, the data points that we have are highly dimensional. And in statistics, highly dimensional or something that has more than one dimension is called multivariate. That's just their terminology. And multivariate data just means that we have random observations, that come from some process that we don't understand. And these observations, for example, the frequency of withdrawals and the average size of withdrawals, they're not completely independent of each other. They're correlated among each other. They have a lot of structure in them. So these, and we denote these multiple observations that we make in such a data point as a random vector. That's what you can see here. This is a random vector, and basically each of these elements in such a vector is a random variable. And the random variable is a precisely defined mathematical concept, but if you haven't heard statistics or stochastics yet, it's completely fine to think about a random variable just as a variable that can take random values. So that's absolutely enough to know. And then we have multivariate distributions. Now we have probability distributions in this high dimensional space of where the data is coming from. And we denote these probability densities also then in this way by having them, all of these components basically as an argument to this distribution, or in a short form as a vector. So what does it mean? A probability density P, what does it mean? So this probability density in itself is very super small. Now you can only interpret this probability density if you multiply it with the size of the region that you're interested in. Yeah, for example, you're looking at the probability that the temperature is 32.7678 and so on degrees. Now that's a real number, and you will have 0 occurrences if you ask for this specific real number. Yeah, to observe this specific real or irrational number, for example, in your data. Yeah, what you rather are looking for is what is the probability that the temperature is in a certain interval. Yeah, and then mathematically you set this interval to something very small. And this is why you can only interpret the product of this probability density with some small interval. Yeah, that's a mathematical thing. It's not super important for understanding what's going to come. And the multivariate extension of this idea of intervals and how to interpret probabilities, we can see on the right-hand side. Now you're looking at some cube or some square in a 2-dimensional or higher dimensional space. You know, to basically count how many the fraction of observations that you have in this little cube or hypercube in the dimensional space that the data points come from. Okay, so far so good. Yeah, so example is a multivariate Gaussian distribution or normal distributions. Probably you've also seen a normal distribution, you know, the classical bell curve. The multivariate extension of this is this one here. Yeah, so basically, probably it's if you look at this formula above here. Yeah, so then you have here something that is quadratic, yeah, like in the normal distribution, yeah, in the univariate or one-dimensional. Now this is quadratic in x, so you have one x here and one x here. Yeah, so this quadratic in the normal distribution is still there, but you replace that with something more complicated now because you're in this high-dimensional space, which is so-called bilinear form. Yeah,
T is for transposed, right?
T is for transposed, yeah, and the way of how to read this entire formula is down here. That's the bilinear form. You've probably heard that if you had linear algebra lectures. It's a way of multiplying 2 vectors together with a matrix. And in our case, this matrix here encodes the variance of the standard deviation of the data. Yeah, this plus on top of that, how the different dimensions of the data co-vary with each other. Yeah, they're not independent. That also has information about how the different dimensions of the data set relate to each other. Yeah, so this is just how you can think about more than one-dimensional distributions. And of course, this intuition doesn't work that well in more than 2 or 3 dimensions. Now, when I talk about distributions and data points, what do we actually mean by this? Yeah, what is a data point that is drawn from some distributions? From some distributions. Now, in statistics, there are 2 ways of how people, different philosophies of how people think about what it means to draw a value from a distribution. The frequentist school assumes that this distribution that we have, like the one on the previous slide, is something real and true. Yeah, so the data points are drawn from this distribution that is the reality. And then this distribution that we represents relative frequencies of how often I find different data points, yeah, in an experiment, for example. Yeah, in the frequentist view, these distributions are real objects, they are the truth, yeah, and when we sample from them, when we draw values from these distributions, then we sample from this real distribution that we somehow, when we sample more and more, we approximate this real distribution. There's another view, that's the Bayesian view. And this Bayesian view states that only the individual data point exists and the distribution is, so to say, not a true object. And what the Bayesian interpretation of this distribution is that it encodes our degree of belief in finding a certain outcome. Yeah. So a typical interpretation of the frequentist view would be, no, this is a typical percentage. Yeah, it's a percentage. So what is the frequency of observing? What is the frequency of observing 10 times hat in my next experiment, coin flip experiments? The Bayesian view is more about a hypothesis. Yeah, what is my degree of belief in that a certain smoker will get cancer in 10 years or so? Yeah, that's the typical Bayesian way of seeing things. Mathematically, they're of course very similar and almost identical, except when you talk about uncertainties. How do I quantify uncertainties? How do I reject a model or not? That differs between these different views, and they take different tools of quantifying these things. For example, in the Bayesian, in the frequentist view, you have p-values, you have things like 95% confidence intervals, these kind of things. What in the Bayesian view, you have more things like credibility intervals, and different ways of selecting from different hypotheses or models. Okay, yeah, so now let's just note some rules from statistics, and just briefly remember for us all, what actually are some very simple ways of doing computations with distribution. First, a little bit of notations. Suppose we have in the simplest case, two random variables, so bivariate distribution. Then one thing we can define is the conditional probability, the probability of observing y given that the second variable has a specific value x. So this is the conditional probability. What is the probability that someone has cancer given that this person is a smoker? What is the probability that someone has cancer given that this person is not a smoker? We can also have the joint probability, p of x and y. What is the probability that someone, a random person that I pick from the population, has cancer and is a smoker? That's the joint probability. And this joint probability we just get by multiplying the conditional probability. And what is the probability that someone has cancer given that this person is a smoker, times that this person is a smoker in the first place. I hope the smokers don't feel too bad about this example. So there's a joint probability, there's a marginal probability. What is the probability that someone has cancer, regardless of whether this person is a smoker or not? And we can obtain this by integrating or summing over all possible values that, for example, this smoker or non-smoker variable can take. And substituting this above floor, we find that P of y can express this as conditional probabilities. Now, then another important aspect is the aspect of statistical independence. And that means that the conditional probability that somebody has cancer, given that this person is a smoker, is the same as this marginal probability that someone has cancer. So that means that the outcome that someone has cancer is statistically independent, not related to whether this person is a smoker or not. And this is also just equivalent by substituting the above to the joint probability factorizing into two separate distributions. Yeah? That's another way of saying that these distributions are independent of each other. Yeah? And now we have to we have some more rules for multivariate distributions. And the first one is that we can decompose multivariate distributions into something like a chain. Yeah, it's also so-called the same chain rule or decomposition of joint probabilities. And that means that if we have some high dimensional distribution, we can now apply what we learned here, on this slide, for each variable separately. Now, for example, in the first step, we can say that this distribution factorizes first into one conditional probability of xd, so the last dimension, conditional on all the other dimensions. And so on. That the second last variable then is conditional on xd minus 2, x1, and so on. And the second, the first variable is like this, and then only the first variable is left. Now that's how we can apply the rules on the last slide, dimension by dimension, to decompose the complex joint probabilities into a chain of conditional probabilities. Now there are certain special cases for this, and the first special case is if we have something that's called a Markov chain. And a Markov chain is a probability vector where each element only depends on the previous element, but not on any other element. Classical example is time series or stochastic processes in time, where usually the assumption is made that the state of this process only depends on what happened immediately before the current moment of time, but not on the entire history in the past or the future. Yeah, Markov processes are very extremely important to the stochastic process, so the time evolution of such random variables. Now, if we have such a Markov chain, then this joint distribution factorizes into terms, into factors that only depend on, so to say, the neighboring one direction element. Yeah. This way, P of d minus 1, x d minus 1, that only depends on the state at in the dimension d minus 2, and so on. P2, x2 given x1, P of x1. Now, and then we have another special case that is important, namely statistical independence in all of these dimensions. And then we can again apply the rule from the last slide for statistical independence and see that this then factorizes into all kinds of into separate probability distributions that only depend on this one dimension and one dimension at a time. Yeah, PD of xd, PD minus 1, and so on. P of 1, on X1. Yeah, so that's the most simple case that we can have. Now, there's another rule that is very important, namely, it's called Bayes theorem. Yeah, and that's what we will use for classification today. So as a reminder, on the previous slide, we can factorize the joint probability of two variables into a conditional probability times the marginal probability. Yeah. So here we can factorize this joint probability. The probability that someone has cancer, given that this person is a smoker, is equal to the joint probability that somebody has cancer and is a smoker is equal to the probability that someone has cancer, given that this person is a smoker, times the probability that someone is a smoker. Now that was the simple decomposition of the joint probability, and that's a representation on here on the left-hand side. But of course, we can also say that the joint probability is completely symmetric in exchanging the arguments. So the joint probability that someone is a smoker and has cancer is the same as the joint probability that someone has cancer and is a smoker. Yeah, so that's these two probabilities reflect exactly the same thing. And because this is the case, we can equate the terms on the left-hand side and on the right-hand side and obtain what is Bayes theorem. Yeah, so that means that P of y given x is equal to P of x given y times the probability P of y divided by P of x. Yeah. So, and this is extremely important because it tells us that we can describe or predict the probability that someone has cancer, given that this someone is a smoker, by the probability that someone is a smoker, given that this person has cancer. Now, it allows us to exchange the conditions in this conditional probability. And the only thing we have to do is we have to define the marginal probabilities. And this is very important for all kinds of statistical inference tasks, model inference tasks, and so on. Yeah. And very often we know the blue, the right-hand side of the blue term, the blue probability, but not the red probability. Yeah, and because of this formula, this tells us that if we know the blue probability, we've gone already a far way to knowing the red probability. And now let's give this first a box because it's important. But also let us give these names, these terms, some names. Yeah, the left-hand side is, so to say, the outcome, the final thing, the final probability that we want to learn, and that's why it's called the posterior probability. It's called the posterior. Yeah, that's the posterior. What else do we have? The marginal probability here. Is the probability that someone has cancer in the first place, even before I know anything about whether this person is a smoker or not. Yeah, and that's why it's also called a prior probability. So what do I expect? Some random person, without knowing anything about this person, to have cancer. That's the prior probability. And then this one here, the likelihood. Yeah. And the black term here is basically, it's called evidence. But for our purposes, it's just a normalization factor, because this is the same thing as x, y, p of y times dy. Now it's just the normalization of this posterior. Yep. And okay, so what do we have here? Now the posterior, we have the likelihood and we have the prior. If we think about the Bayesian terms, in Bayesian terms, we can use this to test different hypotheses. Now the blue thing is, what is the probability that my hypothesis is true given some observations? Now, what is the probability that my hypothesis that you're a smoker is true given some observations of your skin color or so? Yeah, that's the red thing. And now the blue thing, the likelihood, allows me to turn these things around and say, what is the probability that you're a smoker? So what did I say about the red thing? I always turn these things around. Okay, what is my probability to have an observation now that you're a smoker, given that my hypothesis is true? I should start from scratch. I've confused myself. I can't remember what I said about the red thing or how I turned things around.
You can write x equal y equal.
Yes, let's do it. We have to do it here. Okay, so let's say that x, so y, is a hypothesis. For example, yeah, what can be a nice hypothesis? For example, in a medical context, yeah, that someone has cancer. Yeah? X is an observation or some data. Yeah, some medical imaging that I do of some tissue of you, or also some other information that I have. Yeah, for example, I can do a NMR or some brain scan or so, some observation that I've.
So x is really an input. Then
Yeah, you
y
can
is a function applied to this input.
So you can think about it as, if you think of it in the Bayesian way, y is a hypothesis that I have. For example, what is the probability that a certain hypothesis, that P of y, will be what is the probability that a certain hypothesis describes a certain observation? So the left
The
side.
hypothesis, then, sorry, I need to make a hypothesis on a given data. So I have to apply a certain algorithm that tell me the data will be something.
Yeah. So for the hypothesis could be just a statement that I have. Yeah, person X, yeah, the patient that is in front of me has cancer. I want to test it. I don't know if it's true or not, but I want to calculate the probability that this hypothesis is true. Now, my degree of belief, that's the Bayesian view of the seeing things.
So without even, so before even looking at data.
Before even, after taking everything into account, yeah, the red one is having taken everything into account. I have looked at the evidence, and now I want to calculate the probability that a certain patient is a cancer patient. Classification problem. Now we're getting slowly into this. Yeah, what is this? The probability that this patient has cancer. And now I make some observations. Yeah. I have a certain combination of these X values, all kinds of medical records, all different kinds of measurements that I do. You know, some blood tests or so. And now Bayes' theorem tells me that I can calculate this probability by turning things around and saying, so if this patient had cancer, if this hypothesis was true, what would be the probability that I would observe a certain combination of measurements. And that allows me, the blue thing allows me to make a model. Yeah, for example, I could construct a model of how a tumor in the blood or so, yeah, change the blood, the measurements of these blood things that are in the blood. Yeah, how do you call that things? Yeah, all these different, yeah, so what they measure in these blood tests, yeah, some hormones or so. Yeah. Yeah, the blue thing is something that I can predict with a model. I just have to find the model. Yeah. And to have a model, I don't even need to understand things. I can just fit a statistical distribution or so. Now, the blue thing is something that I can easily calculate, yeah, as a statistician or a theorist. The prior is also something that I can calculate. I can make assumptions about what is the general proportion of people in the population that have cancer. Yeah, before I start any measurements, what is the prior probability that someone has cancer? Yeah, so the Bayes theorem in this case allows us to test the hypothesis by using a model. That's why it's very helpful for us. Now we use this theorem also not only in machine learning, but also if we in the group do modeling of some biological system. Yeah, we want to know whether a certain model is correct. Yeah, the right-hand side. Yeah, does a certain model, a combination of parameters, describe some experiment that we see? And the only thing we have to do is to calculate the blue things. If we have a model and we run a stochastic simulations or so, what is the probability that the simulation gives me something that looks like the experimental data? Yeah, this possibility to turn these conditions around, that's the power of Bayes theorem. Now, here, we want to apply this Bayes theorem, the first instance, to classification. And classification means we're going to calculate the red thing on the previous slide. What is the probability that a data point that we see belongs to a certain category or class CK? Yeah, what is the probability that a certain email, a given email, is a spam email? Now, Bayes' theorem tells us that we can turn this conditional probability around. Now, the probability that an email is a spam email, given the words in this email, is just the probability of finding a certain arrangement of words, given that an email is a spam email. And now I just need a model that predicts spam emails. And I can calculate the left-hand side. Now that's the usefulness of Bayes' theorem. So we have here again Bayes' theorem. The thing in the nominator is something that we need to calculate. The thing in the denominator does not depend on the class or on the category, spam or not spam. It just depends on the email, on the data, but not on how I categorize them. So this thing in the bottom, in the denominator, that's not relevant for the classification problem. It's just a prefactor that doesn't depend on how well I classify a certain email. Yeah. Now what we can do, so this is Bayes' theorem. And in order to classify emails into spam and non-spam, we can just use the decomposition formula and say that P, now that the yellow, the thing that we're interested in, P of X, given a certain cluster, a certain category, Ck times P of Ck, which is the joint probability. Yeah, I'm just applying the basic rules for distributions. And now I can decompose this joint probability as before. Where is it? Here. Decomposition of probabilities. Now I just apply this formula and get that P of x1 conditioned conditioning on x2, xd, but also on the category times P of x2 depending on x3 and xd and the category multiplied and so on by P of xd dependent of ck times P of ck. Yeah, so I now just apply this decomposition. Now this is pretty complicated. Yeah, so this is still a high dimensional thing and extremely difficult to calculate. And specifically to calculate this, we would need a huge amount of data. Yeah, we would need to calculate histograms in a huge number of dimensions. And then the probability or the possibility that in any of these dimensions we have not a single observation is quite high. Yeah, so this is not something we want to deal with. Now in this naive Bayes classifier, that's where the naive Bayes classifier gets its name from, we make a very simplifying assumption. It's a most brutal assumption that you can make, namely that all dimensions or all features in our data points are statistically independent of each other. Yeah, in the bank example, that would mean that the frequency of withdrawals is statistically independent of the size of withdrawals. It's a brutal assumption, and this assumption just means, and that exactly it's already written here, that we can write this conditional probability that previously depended on all other dimensions in X, that this conditional probability now only depends on the class or the category. Yeah. And if we have that, we can say that P, the left-hand side from our Bayes theorem, the class or the category, depending on a data point X, yeah, which was proportional to the joint probability. Now I'm leaving away this denominator because it doesn't change anything in the classification. And this was again proportional, now applying this decomposition to P of ck, P of x1 given ck times P of x2 given ck times P of xd given ck. Now this is just a long product. Now we can more compactly write this as P of ck, yeah, times product over all other dimensions. P of xi given ck. Now, this looks much more simple. And now how can we use that for learning? Now, on the left-hand side is what is the probability that a given data point belongs to a certain category. And on the right-hand side, we have something that is now a simplified version of Bayes' theorem. We have the prior. What is the probability to find this category in the first place without any data? And something that we can predict if we know where these categories come from. Yeah, so now the bank just has to hire someone who can make a statistical or stochastic model of credit card fraud. Yeah. So now we have this, yeah, so we can predict this probability. I'll show you in detail some ingredients that are missing, especially how we get this conditional probability here. But now we have to select a rule to transform this probability to a classification rule. So, and there's of course many ways of how we can do this. And one way to do this is probably what makes the most sense is to use the maximum a posteriori rule. We just pick the class for every data point. We calculate what's on the left-hand side, the posterior. We calculate the probability that this data point belongs to a certain category. And we calculate that for all categories that we have, that we can think about, fraud or non-fraud. And now we just need to pick the category that has the highest probability. Now, it's a very straightforward rule. And the way to depict that is that the category that we write this down is that say that the category Y is given by the arg max over the categories K times this formula for the posterior P of CK times I equal 1 to D P of XI. Yeah. So we take the category that has the highest posterior probability. Now, in order to calculate this, we have to calculate the left-hand side, the right-hand side. And in particular, we need to fix these two probabilities that appear on the right-hand side. Now, first, there's this prior probability. That's P of CK. What is the probability that we find a certain category in the first place, a priori? So what is this? And there are some obvious choices. There's a whole literature of how to choose the best prior. An obvious choice would be to say that to pick equiprobable classes. To say, okay, every category or every class has the same a priori probability. There's nothing that would let me favor one class on top of any other class. That means that P of CK would be a constant, would just be a number, 1 over the number of classes, for example. Yeah. Another way to choose, to select this prior probability is to say that I have some training data. And the prior probability is just the relative abundance of samples from the training data that belongs to the category. I can take, so to say, the training data as a prior. Get for training.
It relies on the fact that you have a good representation of all the cases.
Exactly. Yeah. So that's of course the problem, and that depends on the specific data set at hand. If you can make this assumption. Okay. The thing that is less straightforward is this conditional probability on the right. That is this decomposition of these likelihoods. Yeah? So here, this is the probability to find a certain data point, given that it belongs to a certain category. Yeah? Given that I have fraud, what is the probability to find a certain combination of average withdrawals and withdrawal frequency? Yeah, and to get that, I need a model of a fraudster. I need to predict what would be the distribution, the probability distribution of withdrawals and frequency of withdrawals if someone is a fraudster. I need to model for this. Yeah? And this model, yes.
You're talking about a model, you're talking about this probability of finding X given CK, right?
Exactly. And exactly. So there's a little bit of confusion about also the statistics. So we're here physicists at this institute, and for us, a model is something that has some explanatory, planetary power that makes a prediction about some perturbations and so on. Statistics, a model is any distribution. Yeah, regardless of whether it's a true reflection of reality or not. That's just, they call a normal distribution a model. Yeah, in physics, we wouldn't do that because the normal distribution doesn't tell us anything where the data comes from and why it has this normal distribution. Usually, in our case, a model would involve some differential equations or so that have a meaning on where the parameters have an attachment to reality, but in the field of statistics, a model is something, it's just a function or a distribution. It's just some name. Yeah. But we can, if we're interested in the problem of classification, then we can take either approach. Yeah, we can say, okay, we understand fraudsters. I make a stochastic model of fraud. Yeah, and because we're supervised learning, we have data about fraudsters. Yeah, so we know how many withdrawals fraudsters make and so on. Yeah, and I can then write down some stochastic differential equations or something like this that predict the probability distributions of withdrawal given that someone is a fraudster. Yeah, and then I can predict the right-hand side. The other way is to say, okay, I don't know where the fraudsters, why they go to the cash machine and it's this frequency or what they're doing there. Yeah, but I just take a normal distribution or some other distributions and fit it to the data. And then I hope that it describes future events equally well. That's the other approach, but in any case, now that's again the power of Bayes' theorem, we can now have a model of what fraud looks like and predict if someone is a fraudster. So we need a model for each class. We need a model for the fraudster, and we need a model for the ordinary customer. Now, as this is a sub-branch of statistics and not physics, so the models that people usually talk about are statistical models. Yeah, so these are models that follow some distributions without saying where these distributions come from. And here are two distributions that people typically assume. First, if the data, like in the fraudster model, if the data is real and continuous, then people very often take a normal distribution to describe each class. And this normal distribution has parameters. For example, the mean and the variance, or the standard deviation. And now what I have to do is to take the samples in the training data that belong to a certain class and fit the mean and the variance for each class or category. Yeah, with the mean and variance of the withdrawals of fraudsters, and what are the mean and variance of the withdrawal of ordinary customers. Yeah, and that's something you can get easily from the data. And of course, that's simplified by the fact that we assume here that the different dimensions of the data are completely independent of each other. So for each category, we have to solve, so to say, just one-dimensional problems. And for each dimension, we can treat each dimension separately. Now, in some cases, we have count data. Now we recount the frequencies of some events. I'll give you an example later. And if we have count data, yeah, so if I have a coin flip, if I have a coin and I want to know the number of heads or tails. Yeah, so that's this count data that has integer numbers. Then in the coin flip example, I get a binomial distribution. Yeah, but if I have many connected coins, yeah, or multi-dimensional coins, then we don't have a binomial distribution, but a multinomial distribution. Yeah, and this is depicted here. It looks a little bit like the binomial distribution. Yeah, it's a little bit more general. And this multinomial distributions are usually are often used to describe count data. Now, then we can have data that is binary. Yeah, that's just 0 or 1. And then we can take Bernoulli models, yeah, that describe such binary data. Okay, so typical example, as I said, spam filtering. And actually Bayesian classifiers are used to detect spam filters, to detect spam emails. Yeah? So we need to classify emails into spam and not spam. And what is typically used, and also in other tasks of text or document classification, are tables that give us the number of occurrences of certain words in these emails. Now, so our data point has one dimension for each possible word. Now, of course, many dimensions, and the value in each of these components of the vector is the frequency with which we observe in a given email. Yeah. And now we're back to counting. Yeah. So now we're back to counting, and here we're counting words. And a typical model that is then used in this example is the multinomial model. Yeah, so this extension of the binomial model that describes higher dimensional counting data. Yeah. This is how the distribution looked like. I just copied that from the previous page. And the parameters that we have here are these P of Ki. Yeah, in the binomial case, this would be the probability to flip to find head or tail, for example, 50%. In the multinomial case, we would need a higher, would need to fix this parameter for every dimension. But we can easily get this, the probability of heads and tails, by just counting how many heads we got in the training data divided by all samples in the training data. Now, if we have in our training data 50% heads, 50 heads, and out of 100 coin flips, then this P would be 0.5. Now, it can be very easily calculated from the data by counting the number of occurrences divided by all the total number of observed words. And then you get tables like on the right-hand side, that have the frequency of the frequencies or the probabilities of certain words in spam emails for each of these categories, in spam emails and in ordinary emails. Yeah, so this is used for spam filtering, and this fixes this this conditional probability. And because we have this conditional probability here, we can then go back and calculate the posterior probability and look for the maximum for each email, look for the maximum posterior probability and assign this email as a spam or non-spam. So for each email, we calculate these terms here and we fix the parameters of our distribution of our model and the training data. For each email, we calculate what is the posterior probability that this is spam or not spam. And then depending on which probability is higher, we move this email to the junk folder. Yeah, so that's how classification, naive Bayesian classification works for me. Now, this is a super simple approach, yeah, but it works surprisingly well. What are the advantages and disadvantages? One advantage is that because of this strong assumption, yeah, that all the dimensions have nothing to do with each other, you can treat each dimension separately. Now you don't have to fill this super high dimensional space, you know, of words and emails, for example, with all kinds of, yeah, so you ignore this in the case of emails, you ignore the position of words with respect to each other. Yeah, so you ignore that, for example, after the word is, you very often have the word for example. Yeah? So that certain words come together at higher frequencies than you expect just by statistical independence. You ignore that, but by ignoring that, you can solve, so to say, the problem at the fit for each dimension, for each word separately. Yeah, and that is a huge benefit, and that's why it requires less training data than other classification algorithms. It is very fast. You don't have so much this curse of dimensions, that the higher your dimension, so the runtime of these classification schemes increases linearly with the number of dimensions, which is very good. It's not exponentially. And despite this super rough approximation, it works reasonably well in a lot of instances. Now, what this is very bad and what you shouldn't use it for is to use these models to make predictions, to draw. So you fitted this model to the data. For example, using a normal distribution, you shouldn't use this to generate new data. It's not good for making predictions.
What do you mean? Because here we're talking about classification. So
yes, exactly. But you could also, once you have this model, now you could also use it for making predictions about virtual fraudsters, for example. Yeah, you could think about using that, of doing that. Yeah, but if you planned doing that, it would be a bad idea. Yeah, so that's a downside. Yeah, and exactly, that's indeed used for practical applications for document classification, spam emails, also in marketing or customer classification and so on. And because it's a very simple algorithm and very fast. Okay, so next week we'll continue. I think I'm ending on time pretty good.
For example, it would be a very bad way to generate spam.
Exactly, yeah, because also because of this assumption, yeah. So the prediction of spam emails make is garbage. Yeah? Just
sentences and so on.
Exactly. Yeah, but that doesn't mean that you cannot use it to classify text emails. So that's okay. Great. Yeah. So next week we'll continue with further classification methods, namely random support vector machines. And after that, we'll continue with regression. It's prediction of real valued data at neural networks. Okay, great. I'm very happy that I'm finished on time. And first time. And now I'm making up of all these extra minutes from the last lectures. Okay, great. So if you have any questions, just shoot.